If we compare this theorem with theorem 27, there are slight differences. In theorem 27, we add or subtract or multiply the same integer on both sides, like a plus c and minus c and times c like that. But in here, a is congruent to b modulo m and c is congruent to d modulo m. Then it's kind of extension of theorem 27 or more generalization of it. So not only just same number, but if you keep the same congruency, then you can add on both sides with different integers which has same congruency, then we still keep this congruency between these two results. And that is true for addition, subtraction, and multiplication. So this is a more powerful statement. And theorem 27 is kind of consequences or corollary of this theorem. So let's try to prove it. Okay, our assumption at this moment is A is congruent to B modulo M and C is congruent to D modulo M, which means A minus B is a multiple of M. So for some integer k, A minus B is equal to mk. So for the same reason, C minus D can be written by M times L for some integer L. Okay, then let's look at the first one. Given condition is A is congruent to B modulo M and C is congruent to D modulo M. The meaning is, but with that condition, let's start with A plus C minus B plus D. Don't ask me, just that's what the results we want to prove, right? So just let's thinking about that subtraction between these two numbers. Then after you arrange it, this number is equal to A minus B plus C minus D. But in this condition, we say because of that, A is congruent to B modulo M, A minus B can be written by M times K. So instead of that, we can say M times K. Plus, instead of C minus D, we can plug M times L. So this A minus B plus C minus D equals M times K plus L after factor out M. Then the form looks like this left hand side is multiple of M. So by the definition, we can say A minus, because this subtraction is multiple of M, right? So altogether we can say A plus C is congruent to B plus D modulo M. So that's the conclusion of the first case. Second, start with the same condition. Then now we start with A minus C minus B minus D. Then after arrange it, we have A minus B minus C minus D. Please check by yourself. And of course, A minus B, C minus D is a multiple of M. So this should be can be written by M times K minus L. So the meaning is this subtraction is actually multiple of M. So by the definition, we can say A minus C is congruent to B minus D modulo M. That's the second case. The third one is, how about AC minus BD? Then we can subtract B minus C and add, subtract BC and add BC. So it doesn't change anything. It's just same as AC minus BD, like as in left hand side. So we can keep this equality between these two. But from this case, from here, we can factor out C remaining A minus B. And from here, we can factor out B and remaining C minus D. So we got this part. But we already have A minus B can be written by MK and C minus D can be written by ML. So this one is equal to C times MK plus B times ML. And we can factor out M. So is equal to M times ck plus bl, and all these numbers are integers, so all together is a one integer, which means ac minus bd is a multiple of m. So by the definition, ac is congruent to bd modulo m. The corollary of that is going to be like this. A, B, K, M's are integers and K, M's are positives. Then if A is congruent to B modulo M, then A to the K is congruent to B to the K modulo M. So if you just multiply A K times, is congruent to the B is multiplied by K times. And in our lecture note, we give some other style of proof. But if you look at this third case here, if you have same congruency, then you can multiply side by side. So A is congruent to B, and if A is congruent to B here, then this result tells us A square is congruent to B square modulo M. And you can do again. So you can multiply as many as K for this side and B is on this side. We can still keep this congruency. So that's the result in this corollary. If you have that, then you can multiply A a certain number of times and do the same thing for B. We still keep this congruency between them.